Welcome to The Explainer. Today, we're diving into something I found absolutely fascinating in our source text. We're going on a bit of a dual journey. First, we're going to decode the physical architecture of computer memory, but then we're going to flip the script entirely. We'll look at the actual linguistic tricks the text uses to teach us those very concepts. It's hardware and language all rolled into one. Let's get into it.
So think about this for a second. A computer processes massive amounts of information, right? But how does it know precisely where to find just one single piece of data in a fraction of a second? This is the fundamental difference that separates active processing from just, mere remembering. To really understand how a computer pulls this off, we've got to look under the hood at its underlying anatomy.
Here is our roadmap for today. We'll start inside primary memory, look at expanding capacity with secondary storage, compare sequential and random access, unpack the virtual storage illusion, and finally, decode that technical text architecture.
Section 1. Inside primary memory. Let's start right inside the tight, high-speed confines of the CPU. This brings us to primary memory, which is often called real or internal storage. Its entire job? Temporary storage. It is all about speed and random access. It gives the CPU exactly what it needs, right when it needs it, so it literally never has to wait around.
Now, in the source material, you'll see capacity expressed in quantities of K, like 16K or 152K. And while we know each K is exactly 1024 bytes, I want you to pay close attention to how the author uses these specific, concrete numbers to really ground the abstract concepts we'll see later on. The source text uses a really brilliant analogy here. It describes these storage locations as a series of tiny compartments, where each one has its own fixed address. It's exactly like houses on a street. These digital addresses never change. Because they're fixed, the control unit knows exactly where to dash in, read the data, or wipe it clean at absolute lightning speed. Section 2. Expanding capacity. Secondary storage.
So while primary memory is incredibly fast, it introduces a pretty massive hardware problem, and that is cost. Because it's so expensive, it's really only used transiently. To process vast amounts of data, computers are forced to rely on secondary memory. This steps in to provide massive capacity at a much lower cost. It's essentially a calculated trade-off with that blistering primary speed.
Section 3. Sequential versus random access. When we look at the two main categories of this secondary memory, there's a fascinating physical trade-off happening. On one side, sequential devices like magnetic tape are super cheap, but the machine literally has to spool through all the preceding data just to find what it needs. It's slow. On the other side, random access devices like magnetic disks permit almost direct access. They just bypass the irrelevant data entirely. It's way faster, but naturally a lot more expensive.
Section 4. The virtual storage illusion.
But what happens when a demanding task requires more primary memory than you can actually afford? Well, this is where computing gets incredibly clever. Through something called virtual storage, the system essentially tricks itself. You hook up secondary magnetic disks, the system treats them as a direct extension of internal storage, and boom, it simulates increased capacity. A machine with only 256K of real storage suddenly operates like it has 512K. It effortlessly bridges the gap between physical limits and processing needs. It's kind of like magic.
Section 5. Decoding technical text architecture.
Okay, so we've solved the hardware problem. Now let's pull back the curtain. How did the text actually teach us these highly technical concepts without losing us? Notice how the writer explicitly uses connective markers, phrases like "for example" or "an example," to systematically anchor abstract terms to concrete facts. When they explain a tough concept like virtual storage, they immediately ground it with a real-world scenario. You see, these aren't just filler words, they are structural signposts letting your brain know that reality is about to kick in. Authors also construct arguments using very specific logical flows. In a deductive presentation, they'll hit you with a broad rule first and then back it up with examples. Conversely, an inductive presentation gives you specific clues first, kind of building suspense right up to a broader generalization. Recognizing which path the writer is taking, that's a real superpower. It helps you anticipate the information and absorb complex material almost instantly. To build on this, authors also use exact structural markers to seamlessly layer information without losing you in the weeds. If they want to add weight to a point, they'll use reinforcement markers, like "in addition to." If they're bridging a totally new concept to one you already know, they'll use similarity markers, like "likewise."
Recognizing these cues completely changes how quickly you grasp the relationship between ideas. It's basically a cheat code for reading comprehension.
As we wrap up this explainer, I've got a challenge for you. Next time you learn a complex topic, will you notice not just what the writer is teaching you, but how their linguistic architecture is shaping your understanding? Whether it's computer memory, biology, or economics, start paying attention to the for examples, the likewises, and the structural flows. When you understand exactly how their linguistic blueprints shape your mind, well, it might just change the way you process new information forever. Thanks so much for joining me today.